All right, lesson 4B, polynomial functions and rates of change. So it says, looking ahead to calculus, let's explore concavity. Our goal is to understand the terminology. Later, we'll have rules for finding these intervals. So a function is blank on an open interval if the graph looks like a U or part of a smile. So if it looks like part of a smile, remember that is concave up. And it says shade the graph at the right in green for this behavior. So, and remember it's going to be concave up all the way to some point that's going to be somewhere in between a maximum and a minimum, okay? And then a function is concave down on an open interval if the graph looks like an upside down U or part of a frown. So this is going to be concave down. And it says the graph shaded in blue. So from that point that it changes concavity there, and this one goes all the way to the right to infinity, is where it's going to be concave down. All right, a function f has a point of inflection at C on an open interval if the graph changes concavity. So, as a point of inflection, remember we talked about this the other day, the point of inflection is going to be somewhere between a maximum and a minimum. And so it's where the slope goes from, where it changes from increasing to decreasing or vice versa, the slope of the tangent lines. And so, whoops, it said to do that in red. I did it in blue. Just trying to follow directions a little bit there. So somewhere in between that max and minimum value is that point of inflection. All right, and then if we want to find it, we can take the average of our x's. So we know that our x of the minimum is -2, and the x of our maximum is 3, so divide that by 2. And so we get 1/2. And then if we had an equation, we would actually plug the x into the equation to solve for the y. But they didn't give us a y equation, so we're going to do the same thing for the y's. So the y of my minimum is -6, plus the y of my maximum is 4. Divide that by 2. And so it gives me -2/2, which is -1. So my point of inflection is approximately at 1/2 -1. All right, example 6 says, can you determine how many points of inflection occur in the graph shown below? All right. He says, label the approximate location of each point on the graph, shade the concave up and concave down intervals in different colors. All right, so the points of inflection. So remember, it's going to occur between a maximum and a minimum. So somewhere in here is 1. And somewhere in here is another one, okay? So those are my points of inflection. And then we have this point here, which is a minimum. Up here we have a point, the maximum, and then we have another minimum here. Or we can just call these turning points, okay? Maximums and minimums are turning points. I'm going to call this one turning point 1, turning point 2, and turning point 3. And it said to shade the concave up and concave down in different colors. So let's see. This first part here, we can see that this is making a smiley face. So that's going to be concave up. And then we can see we're making a frowny face here. So it's concave down to that next point of inflection. And then we got a smiley face again, so it's concave up. All right, so point of inflection can occur at one of 3 different places. At a 0 with a multiplicity of 3. So what it means is a 0 is where it's going to be crossing the x-axis, and it's going to have multiplicity of 3. So it's going to be cubic looking. at that point, okay? So cubic looking just means that it's going to be like coming up like this, or it's going to be coming down like this at that 0 right there in the middle, okay? So it's going to have that look. The second thing will be to estimate a possible point of inflection between two consecutive extreme values. So at the midpoint between the relative max and the relative min values, like we just did on the previous example. And we can estimate a possible point of inflection between a 0, multiplicity of 3, and the closest relative extreme value. All right, so example 7. It says, given the graphs below, find the points of inflection by one of the 3 methods stated. Label and identify the coordinates of all points of inflection. State the method you use. All right, so in this first one here, we can see we've got this cubic looking thing going on right there, okay? So that's going to be our rule number 1. So we've got a point of inflection right there due to rule 1. So we have a 0 at x equals, and that's it, x equals 3. So my point of inflection, oh, and I should put here, it's got a multiplicity of 3. Okay, that's gave it that cubic look. So I got that point of inflection is going to be at 3, 0. And then we've also got rule 3 here that says we could have it between a 0 with multiplicity of 3 and the closest relative extreme values. So we have this 0 right here, and we've got this extreme value here. So somewhere in here, there's going to be a point of inflection. So that one's going to be because of rule number 3. And it's because we get that 0 at x equals 3 that has the multiplicity of 3, and we have a relative minimum at x equals 0. And so that 0 has the ordered pair 3, 0. That relative minimum has the ordered pair 0, negative 3. And so we can find that point of inflection. Oops. Remember, take the average of your x's. And the average of your y's. And so this gives us an approximation of the point of inflection there. And so we have 2 of them. We have a point of inflection from the rule 1 at 3, 0, and from rule 3 at 1.5, negative 1.5. All right, on B, we just have a maximum and a minimum here. So that's going to be from our rule 2. This is between 2 consecutive extreme values. This is rule 2. So we have a minimum at 3, and let's talk about negative 2.5. We have a maximum at negative 2 and 5. And so we can find our point of inflection by averaging those points. So the x is going to be 3 plus negative 2 divided by 2. Y is going to be the 5 plus a negative 2.5 over 2. And so an estimated point of inflection will be 0.5 and 1.25. All right, on C, so I didn't graph that last point of inflection. If you were wanting to see where it is, it would be somewhere in between them. Okay, now let me go back to C. So we can see here, this is just rule number 2. It's going to happen twice because I have 2 extrema right here. So I'm going to have a point of inflection somewhere in between them. And then I have 2 extrema here. And so I'm going to have a point of inflection somewhere in between them. All right, so both of these are going to be rule 2. So let's see, my first one, I have a maximum at -4, 4. And I have a minimum at -2, 0. So the x is -4 plus -2 divided by 2. So -6 over 2, so -3. And the y is going to be 4 plus 0 divided by 2. So 4 over 2, so 2. So I have a point of inflection on this one at -3, 2. And then, let's see, I have a minimum for the second one. I have a minimum of -2, 0. And then I have a maximum of 1, 9. So we're going to average our x's. Average the y's. And so it gives me a point of inflection of -0.5, 4.5. And so I wanted to put them together. I know I have 2 points of inflection. The first one we found was at -3, 2, and the second one was -0.5 and 4.5. All right, so let's put it all together here. So example 8 says for the function y equals g of x shown at the right, identify the characteristics. Once the domain, we can see our graph keeps going to the left and it keeps going to the right. There's no holes, no jumps, no gaps going on in our graph, no asymptotes. So therefore, my domain is going to be -infinity to infinity. The range, my graph does keep going up, but it does not keep going down. The lowest point there is, it looks like it's just right below maybe -8. It's maybe like -8.1, and it keeps going up to positive infinity. The type of function or degree is it's a quartic, which is a 4th degree polynomial. Different ways to tell. I've got, it touches or crosses the x-axis to account for 4. We've got single crossings right here. Those are 1 and 2. This is called a double root, or as we say, it has even multiplicity because it looks quadratic, so it counts for 2. So that's 1, this one's 2, and that one's 1, so that means there's 4 total. Okay, now the thing is it's got kind of that W shape, and if they're W shaped, those are the quartics. All right, D wants the zeros in their multiplicity. Just talked about that. So in a way we have a 0 at the -5. We have a 0 at -2, and we have a 0 at +2. And then at -2 is where we said it looks quadratic, so that one's going to have that multiplicity of 2. So multiplicity of 2. And usually you'll see me shorten multiplicity just to be mult, okay? That means multiplicity when I write it. All right, E says intervals where g of x is increasing. So we can see that the beginning of our graph is actually, I'm going to do E and F together here. So I can see this first part of my graph, we are decreasing. And we're going to decrease all the way to right here, which is at -4. So we're decreasing from negative infinity to -4. And then at -4, we start increasing all the way to -2. And then we're decreasing from -2 all the way to where x is 1. And then we're increasing from when x is 1 all the way to the right where x is positive infinity. All right, and so that we can still see our graph here, I'm just going to kind of use that top point to write down the others. You can put it onto your paper. I'll erase my scribbles that I did here. All right, so we are on G. G says the relative maximum. So remember, maximum is a little hilltop. Relative means it doesn't have to be the maximum of the entire graph, although it could be. I can see I have one right there at -2, 0. So my relative maximum is going to be 0 at x equals -2. H wants the relative minimum. And so we've got two relative minimums. I have one right here when x is -4 and it is -3. So -3 at x equals -4. And we have one right here, which is about at, we said that was going to be -8.1 at x equals 1. Oops, hold on. Oh, yeah, I'm sorry. I saw G up there, and I was like, why did I put max? But that's because it's part G, not part H. Sorry. And then I wants an absolute maximum. My graph keeps going up, so that means there is no absolute maximum, so we could just say none. Hold on. I guess there is no I. That was J. I'm sorry. And so I'm on K, the absolute minimum. We do have an absolute minimum. The very bottom of my graph is at -8.1, and that occurs at x equals 1. L wants points of inflection. So we have points of inflection. We can see, we can use our maximums and our minimums. So actually I'm going to erase what I have up here so I have room to write. All right, so let's see, for my L, my points of inflection, I can see I have, just using that rule 2. So we have a minimum at -4,4 and a maximum at -2, 0, which means I have a point of inflection somewhere in between them. All right, so one of them is going to be at -3, 2. I also have that maximum at -2, 0, and then I have another minimum at at 1 comma -8.1. And so that would be at negative 0.5, comma, negative 4.05. So there's my 2 points of inflection. M wants to know where this graph is going to be concave up. So I'm going to go in here to the graph and I'm going to put those points of inflection on here so it's easier for me to see. So we said that we had a point of inflection at negative 3, negative 2. So right in here. And we had a point of inflection at negative 1/2 and negative 4.05. So right in there. All right, so I can see this first part is a smiley face. So this is going to be concave up. And so that's from negative infinity. Let me erase this again over here. All right, so from negative infinity to that point of inflection at negative 3. And then it's going to be concave down. I'm going to jump down, and that's what N asked for. So I'm going to go ahead and put that over there on N. So concave down. Then it's going to go from negative 3 to the next point of inflection at negative 1/2. And then it's going to become concave up again, and that's from negative 1/2 to positive infinity. And that is the end of lesson 1.4.